Hey everyone, I just wanted to pop on here and give you a quick note before jumping into our chapter on ionic compounds. So just so you all know, this is a recording for both Chem 100 at KVCC and Chem 100 at KCC. So I kind of took the best of both worlds as far as the slides go, and so they won't match up exactly with what slides you have posted on your learning platform, but it covers all of the content that you will all need to know for testing purposes and for success in the rest of the semester. So with that, we'll jump in and get started. Okay, so like I said, this is our chapter on ionic compounds, and so what I want to do is start out by a little bit of review about valence electrons. So if you remember right, valence electrons are the electrons in the outermost shell or energy level of an atom, and that means that they're furthest from the nucleus, and because of that, because they're further from the nucleus, which has a positive charge, if you remember right, we have our protons and our neutrons in the nucleus, and so those positive protons make the nucleus overall a positive charge. And then we have our electrons floating around in that cloud, that electron cloud outside. And our valence electrons are the electrons that are furthest from the nucleus. And so we have our positive nucleus, we have our negative electrons, and that attraction is what holds our atoms together. Now, the electrons that are furthest out from the nucleus are going to feel the least amount of pull towards the nucleus because they're further away, which means that those valence electrons are readily available to participate in bond formation and reactions and things like that. And so when we're talking about the formation of ions, like we are in this chapter, we're really looking at what's happening with those valence electrons. When we represent an atom, we can represent it as an electron-dot symbol. In this model, we have, like our examples down here, we have the element symbol. So for hydrogen, we have H, carbon, we have the C, and so on. And then we have a dot that represents one valence electron. So hydrogen has one valence electron, being in group 1, and so we would represent it with a single dot. When we see something like carbon has 4 valence electrons, and so we draw those 4 around it in the electron-dot symbol. Before you can start pairing up electrons, you have to put a single electron on each side first. So if we're looking at carbon, we can see we have 1, 2, 3, 4 valence electrons, and we represent that with 1 on each side of that carbon atom. When we get into something like oxygen, you can see that once we have 1 on each side, we can then start pairing up. We can review this concept by looking at magnesium. So when we think about magnesium as an alkali earth metal on the periodic table in group 2, and you can see it pictured over here to the right, it's a metal, so it's shiny, all of those properties of metals that we've talked about. And we can gather some information about it, like its atomic number, how many electrons it has, what group it's in, how many valence electrons, and then we can work to draw the electron-dot symbol. So if we pull up our periodic table here, and we find magnesium, again it's in group 2, so we have magnesium right here on the periodic table is number 12. And being number 12, we know that it has 12 protons because atomic number is the number of protons by definition. So anytime we're talking about magnesium, we're talking about an element with 12 protons. Because we're talking about magnesium in its neutral elemental form, the number of protons and the number of electrons are going to be equal to one another. And so magnesium also has 12 electrons. Being in group 2, however, magnesium has 2 valence electrons for our main group elements, so 1, 2, 3, 4, 5, 6, 7, and 8. Your group number is going to correspond to the number of valence electrons that you have. We can then work to draw the electron-dot symbol for magnesium. So when we go to draw the electron-dot structure for magnesium, you'll have that elemental symbol, so Mg is the symbol for magnesium, and then we can draw in those valence electrons. Because it's in group 2, it has 2 valence electrons, and so we'll go ahead and do 1 and 2, keeping in mind that we don't pair these up until we have 1 on each side by itself. So once we have that electron dot symbol, we can start to remind ourselves of the fact that elements are in their most stable form when they have 8 valence electrons. And we refer to that as the octet rule. The exception to that would be the period 1 elements can only hold 2 electrons. They're just not big enough to hold more than that. And so we call that the duet rule. But once you have your electron dot configuration, you want to ask yourself, is it easier for this element to gain electrons or to lose electrons to create a full valence octet? So when we think about the options for magnesium to have an octet, magnesium can either gain 6 electrons to become like argon or lose 2 electrons to become like neon. So let's look at our periodic table and I'll show you what I mean. So magnesium is right here, and we said that magnesium and all other elements want to have that full octet to be stable. When I say all elements, I mean all that we are talking about right now. Okay, so if we look at magnesium, magnesium has 2 choices to become like a noble gas, which has that full outer octet. So magnesium could either gain 1, 2, 3, 4, 5, 6 electrons to become like argon, or it could lose 2 electrons, 1, 2, to become like neon. And so when we're thinking about that, it really is easier for magnesium to lose those 2 electrons than it would be for it to gain 6. Let's do the same by looking at the element sulfur. So if we ask ourselves these same questions, so atomic number, electrons, group, etc., let's find sulfur on the periodic table. So sulfur is right here. It's number 16 on the periodic table. It's in group 6A. And sulfur, because it has 16 protons by definition, remember atomic number is the number of protons, and the number of protons is going to equal the number of electrons when we're talking about a neutral atom. And so sulfur has 6 valence electrons because it is in group 6. And so again, those group numbers make it really nice and easy. When it comes to drawing the electron dot symbol for sulfur, we're going to again draw that atomic symbol S for sulfur, and then we need to draw in its valence electrons. So we said sulfur's in group 6, it has 6 valence electrons, and notice how when I draw these, 1, 2, 3, 4, I don't start pairing up until I have 1 on each side by itself. So there's my 4, 5, and 6 valence electrons. Similar to what we saw with magnesium, we're then going to ask ourselves, is it going to be easier for this element to gain or lose electrons to create that full valence octet? And so we'll ask ourselves, what are the options for sulfur to have a full octet? Well, sulfur can either gain 2 electrons to become like argon or lose 6 to become like neon. So if we look at where sulfur is on the periodic table, again, we're right over here, and you can see that sulfur can either gain 1, 2 to become like argon, or it can lose 1, 2, 3, 4, 5, 6 to become like neon. And it's much easier for sulfur to gain the 2 electrons than it is for it to lose the 6, and so that's what it will do when it forms its ion. So coming over here to our electron dot symbols for magnesium, which we know it would be easier for it to lose 2 electrons, and our sulfur, which we know it would be easier for it to gain the 2 electrons. Well, what if these 2 things just did what they wanted to? And that magnesium gave up its electrons to sulfur. What we would get is a compound, MgS, and we would call that magnesium sulfide. That is really what the whole chapter is about. Okay, so when atoms lose, gain, or share electrons, what they're doing is forming either an ionic bond or a covalent bond to obtain an octet. Ionic bonds, which we just saw, are formed when valence electrons of a metal are transferred to the atoms of a nonmetal, whereas covalent bonds are formed when atoms of nonmetals share their valence electrons. Today we're really focusing on those ionic bonds. The tendency of atoms to attain a stable electron configuration is known as the octet rule. It provides a key to our understanding of the ways in which atoms bond and form compounds. A few atoms achieve the stability of helium with 2 valence electrons. Again, we call that the duet rule, and it's really because those first few elements are just too small to cram in 8 electrons right around the nucleus. And so you really need more energy levels in order for things to want that 8 valence electrons, or those 8 electrons. The other thing is that octet rule cannot be used with transition elements. We're going to see that a little bit later on in the presentation. So right now we're just going to focus on ions and ionic compounds and their formation. And so we're going to start out with ions themselves are just charged species in which the number of protons and electrons in an atom is unequal. And so what we saw is when we have a neutral element, a neutral atom, the protons and the electrons are equivalent, right? We have the positives and the negatives balance each other out to form a neutral compound. Ionic compounds are consisted of oppositely charged ions that have strong electrostatic attraction to one another. And so when you see that transfer of electrons, you then have an imbalance between your protons and electrons, and so you get these charged species. We talk about ions in 2 different types. We have cations and anions. Cations are positively charged ions, and so that means a cation has fewer electrons than it has protons. So in this example here, we're looking at the sodium atom. The sodium atom has 11 protons and 11 electrons, right? That's that neutral atom, so they have the same. However, if you look at where sodium is on the periodic table, it's in group 1, meaning it has 1 valence electron, and it's really going to be easier for it to get rid of that 1 valence electron than it's going to be for it to attract 7 more electrons to itself. And so when it gives up that electron, that loss of electron means that we have 11 protons, but now we only have 10 electrons. When that happens, we end up with sodium with a +1 charge, and we refer to that as a sodium ion. By losing 1, 2, or 3 electrons, an atom will form a cation with a completely filled outer shell of electrons. So in the example that we already saw, we had the magnesium atom where we had 2 valence electrons. The neutral atom is going to have 12 protons and 12 electrons to balance each other out. But when it loses those 2 electrons, now it's going to have 12 protons but only 10 electrons, and so you get a charge of +2 on the magnesium ion. Ions which have electrical charges form when atoms lose or gain electrons to form that stable electron configuration. And so when we're talking about metals in groups 1A, 2A, and 3A, those ionization energies are low. Metal atoms tend to lose their valence electron to form ions with a positive charge. And remember what we said about ions with a positive charge. Cats have paws, and so cations are positive. This cat does it much better than I can ever. Okay, on the flip side of that, anions are negatively charged ion, which means that an anion is going to have more electrons than it has protons. And so if we look at the chlorine atom, The chlorine atom has 17 protons by definition, and in that atom it's also going to have 17 electrons to make that neutral. And because chlorine has 7 valence electrons, being in group 7A, that means it's going to be much easier for it to gain 1 electron to become like a noble gas than it would be for it to lose those 7 valence electrons. And so when chlorine forms an ion, it's going to gain 1 electron, which means it's going to have 1 more electron than it has protons, and it's going to end up with that -1 charge. The ionization energies of nonmetal atoms in groups 5A, 6A, and 7A is high, so rather than lose electrons to form an ion, a nonmetal is going to gain 1 or more electrons to get that stable electron configuration. A negatively charged ion is called an anion, and when you name it, you're going to use the first syllable of its element name followed by IDE. The way that we remember an anion, and this is definitely not as exciting as our cation example, but I always like to split it up and say that an anion is a negative ion. So that's how I tell those apart. This is just a summary of the charges that our main group elements are typically going to have. Noble gases are not going to gain or lose electrons because they already have that full outer shell, that full octet. But in group 1A, you're going to have a +1 charge, right? If it only has 1 valence electron, it's going to want to just give up that 1 valence electron. When you go to group 2A, generally you're going to see a +2 charge on those, and then in group 3A, you get aluminum with a 3+ charge. Then when you head over to the right side of the periodic table, you get to group 5A, you're going to see a lot of -3 charge. 6A, you're going to see a lot of -2, and then in 7A, you're going to see -1 for the charge. Notice that in 5A, 6A, and 7A, in group 5A, which has 5 valence electrons, it's going to be easier to gain 3 than it would be to lose the 5. And then that pattern continues in groups 6 and 7. This is just another way to kind of visualize that. And to me, I like this visualization because you can see how group number and charge are really tied together. So if you are on an exam or you're doing a worksheet or you're doing something and you just can't quite figure it out, this is kind of one of those tricks to kind of help you remember. And while it doesn't work for all examples, it does work for quite a few. So we're going to jump into some sample problems. And so the first is we're going to write a symbol and name for an ion that has 7 protons and 10 electrons. And then we're going to do the same and write the symbol and name for the ion that has 20 protons and 18 electrons. So in this first example, we're looking at an element or an ion that has 7 protons and it has 10 electrons. So the first thing that we need to do is figure out, okay, I have an element that has 7 protons and 10 electrons. How do I know what element I'm talking about? Well, by definition, the atomic number is equivalent to the number of protons that an element has. So if we pull up our periodic table, and we say, okay, we're looking for number 7 on the periodic table, we can come over here and we see that nitrogen is number 7 on the periodic table. And so what we'll do is come back to our work and we can say that we have nitrogen. Now we need to figure out what is the charge on that nitrogen. Well, there's 7 protons. Each one of those has a plus charge. There's 10 electrons, and each one of those has a negative charge. And so we see that when we add these up, we get a charge of -3. We can write that up in the corner to represent the charge. Now you might see the charges on ions written as either -3 or 3-. Either one of those is perfectly acceptable, and I would take either one. Now when we look at our other example has 20 protons and 18 electrons, and so as I said before, the number of protons is by definition the identity, the atomic number of that element. And so if we pull up our periodic table once again, maybe, pulling up that periodic table, we can find number 20, and number 20 is calcium on the periodic table, and so we can come back over here and say we are dealing with calcium. Now we can go ahead and figure out the charge. So those protons have a plus charge, those electrons have a minus charge, and we can see that there's 2 more protons than there are electrons, and so that charge is going to be 2 plus. So I have a problem here that says consider the elements aluminum and oxygen. Identify each as a metal or a nonmetal. State the number of valence electrons for each. State the number of electrons that must be lost or gained for each to achieve an octet, and then write the symbol including its ionic charge and the name for each ion. So we're going to start by doing this for aluminum. And so if I pull up our periodic table, the first question is it a metal or is it a nonmetal? And so if we pull up our periodic table and we look for aluminum, aluminum is right here on the periodic table, and even though it's right along this stair-stepper line, remember that we said that aluminum is a metal, and so we're going to call that a metal. That's an exception to that metalloid rule, and so we're going to go ahead and circle that it's a metal. If we come back over here, the next question is how many valence electrons does it have? And we can see that it's in group 1, 2, 3 on the periodic table. It's in group 3A, which means it has 3 valence electrons. Okay, so we said it has 3 valence electrons. So now we have to ask ourselves, okay, well, if it has 3 valence electrons, is it going to lose those 3? Or would it be easier for it to gain 5 to make that full octet? Well, 3 is going to be easier to lose than 5 is to gain, and so this is going to lose 3 electrons. So when we go to write the symbol for that, we would write Al because it's aluminum, and if it loses 3 electrons, it's going to have a 3 plus charge. We call that an aluminum ion. We can do the same thing for oxygen. So let's change colors here. So for oxygen, if we look on the periodic table for oxygen, we can see that oxygen is right here. It's number 8 on the periodic table, and it's on the right side of the periodic table, so we know that it's a nonmetal. Alright, so we can say it's a nonmetal. If we again look at that periodic table, we can see that oxygen is in group 6, meaning it has 6 valence electrons. So we come over here and it has 6 valence electrons. Now, you have to ask yourself, is it going to be easier for it to gain 2 electrons to have that full octet, or to lose 6 electrons? And it will be easier for it to gain, and it will gain 2 electrons. And so because it gains 2 electrons, our symbol is going to be O, with a 2 minus or a minus 2 charge, and we would call that an oxide ion. So when ions form and they have this transfer of electrons, right? Sodium, in this case, wants to give up an electron, and chlorine wants to gain it. When that transfer of electrons happens, we have an ionic bond that's formed. And this happens again when a metal is going to transfer 1 or more electrons to a nonmetal. The sum of the charges in an ionic compound must be 0 overall. So when we have sodium with a +1 charge and chlorine with a -1 charge, that plus and that minus balance each other out for an overall 0 charge, and we get the compound formula NaCl. A chemical formula is the compound it gives us the symbols and the numbers of the atoms or ions in the lowest whole number ratio, and the sum of the ionic charges again is going to give you 0. So let's look at what happens when we look at an ionic compound that's formed between magnesium and chlorine. And I know that we saw this example in class, but let's also go through it again. So we said we were going to form a compound between magnesium and chlorine, and so the first thing that we're going to do is write out those atomic symbols. So for magnesium, we just have Mg. Let's do a different color. We'll make Cl for chlorine. And then the next thing that we need to do is go to our periodic table. Okay, so if we go to our periodic table and we find magnesium, magnesium's right here on the periodic table, number 12. And being in group 2, it has 2 valence electrons. So I'm going to come over here and we will find our purple color, and it has 2 valence electrons. Okay, and then we need to do the same thing for chlorine. So when we find chlorine on the periodic table, we can see it's right here. It's in group 7 on the periodic table, and so it has 7 valence electrons. So we can go ahead and say 1, 2, 3, 4. Again, we're not pairing up until we've gone all the way around. So there's our chlorine. And so we say, okay, magnesium wants to get rid of its 2 electrons, and chlorine wants to gain 1. So if we go ahead and this chlorine takes 1 of those, now this chlorine has 8 valence electrons, and this magnesium still has that 1 left over. It really doesn't want that 1, but that chlorine can't take anymore. And so what we need to do is bring in a friend, and that one has 1, 2, 3, 4, 5, 6, 7 valence electrons, and then it has space to take that, excuse me, that other electron from magnesium. So now magnesium has gotten rid of its 2 electrons, and each chlorine has taken 1, and so we end up with a chemical formula that is MgCl2. And so you'll notice that in a formula, the cation, the metal, goes first. When magnesium loses those 2 electrons, we end up with magnesium with a +2 charge. Each of these chlorines is going to gain 1. And so when it does, each one is going to have a -2 charge. And then we need subscripts to tell us how many, because if we add up these charges, +2 and -1, gives us an overall net +1 charge. And we want to have that neutral overall compound. And so what that tells us, we can go ahead and cross that down and say we need 2 of those. So we have MgCl2. That is our chemical formula. Again, there's 1 magnesium. You don't write 1 as a subscript. It's inferred. And we need 2 of those chlorines. So the subscript after the Cl tells us that we need 2 of that atom to balance out and make neutral charges. Just to reiterate that point, we saw that magnesium lost those 2 valence electrons to the chlorine. We ended up with MgCl2, and again, we represent the number of each element with a subscript after that element in the formula. So when you write an ionic formula, the first thing you're going to do is identify which element is the cation, which is the anion, remembering that metals form cations and nonmetals form anions. You can use the group number of the main group element to determine what that charge is going to be. So for potassium, which is a group 1A metal, it's going to have a +1 charge, whereas calcium is a group 2A metal, and so it's going to have a +2 charge. From there, you can determine how many of each ion type is needed for an overall charge of 0. If the cation and the anion have the same charge, then you're only going to need one of each to balance one another out. So if you have potassium, which is going to have a +1 charge, and chlorine, which is going to have a -1 charge, then potassium chloride, KCl, you're only going to need one of each of those. Same thing when you're dealing with a compound forming between calcium and oxygen, or the oxide ion. You're going to have a +2 and a -2 charge that are going to balance each other out to give a net 0 charge. However, sometimes you have cations and anions that have different charges, and so you're going to use those charges to determine how many ions of each are needed. So with calcium, you have a +2 charge. It's going to lose 2 electrons, being in group 2A, to give it that +2 charge. And for chlorine is in group 7A, and it's going to want to gain 1 valence electron to make it that full octet. But when you add those together, the +2 and the -1, you end up with a +1 net charge. But you can't have that. You need a neutral atom overall. And so you need 2 of those chlorine ions to balance out the charge. And that's why you get CaCl2. To write that formula, you're going to put the cation first and then the anion. When you write that final formula, you have to clean it up by getting rid of the charges. And so you get rid of the charges, you just leave the element itself, the symbol, and then the subscript to make the overall 0 charge. If no subscript is written, then it's assumed to be a 1, like we said before. So in KCl, you wouldn't write like K1Cl1. That would also be incorrect. So we're going to do a couple of practice problems here. We're going to write the formula for ionic compounds that form from the following elements. Alright, so the first compound that we're going to form is a compound that forms between lithium and sulfur. And so the first thing that we're going to do is find lithium on the periodic table. So we come over here and we see lithium is in group 1A. And so we know that it's going to have 1 valence electron. So because lithium has 1 valence electron, it's going to want to lose it, and so when it does, it would have a +1 charge. Now if we do the same thing and look up sulfur, so we come over here, sulfur is right here on the periodic table. It's in group 6A, meaning it has 6 valence electrons, and so it's going to want to gain the 2 electrons. When it gains 2 electrons, it's going to have a -2 charge. Okay, so from here there's a couple things you can do. One, if we add those charges together, we're going to see that overall that would have a -1 charge, and we can't have a -1 charge. We want to have a neutral compound, and so we have to figure out what's the least common multiple between 1 and 2. Or you can do this nice little trick where you just cross these two. Whoops. You just cross these two, and you would get Li2S1. But remember that when it's a 1, we don't include the 1. And so this is actually Li2S. When we go to name this compound, we just name the first element, and then we replace the end of our anion with IDE. And so when we do that, this would be lithium sulfide. Okay, our second one that we want to form is a compound between potassium and nitrogen. And so we got potassium and nitrogen. If I pull up my periodic table, and I see, okay, potassium is right here. It's in group 1. It's going to have a +1 charge. And if I look up nitrogen while I am here, nitrogen is right here. It's in group 5. It's going to want a +3 charge. I'm sorry, a -3 charge. So we said potassium in group 1 has a +1 charge. Nitrogen, being in group 5, has a -3 charge, and so we know, based on this little crisscross rule, that it's going to be K3N, and when we name that, it would be potassium nitride. Next is magnesium and bromine. So we have magnesium, we have bromine. Magnesium, just for sake of, I guess, speed, I'll just go ahead and tell you. Magnesium's in group 2, so it would have a +2 charge. Bromine is in group 7, meaning it would want to gain 1 electron, and it would have a -1 charge. And so we would have MgBr2, and when we name that, we name it magnesium bromide. Finally, we have aluminum and iodine. Aluminum is going to have a +3 charge. Iodine will have a -1 charge. And so we would end up with Al(I)3. And we would call that aluminum iodide. Okay, so just to review that naming concept that we just talked about, you're going to write the name of the metal ion. It's going to be written first. It's the same as its elemental name when you write it out. And then for the name of the nonmetal ion, or the anion, you're going to write that last, and you'll use the first syllable of its element name followed by IDE. And then a space will separate the name of the metal and the nonmetal. And we just saw that for all of these examples here. So we ended up with lithium sulfide, potassium nitride, magnesium bromide, and aluminum iodide. So up until now, we have only looked at ion formation with elements from the main group elements or the representative elements. That's that group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. But there are other there's other elements out there, right? What about things like iron or copper? Those are transition metals, and we said we can't use the octet rule to help us with transition elements. Usually these elements can form 2 or more positive ions, and transition elements lose electrons, but they're lost from the highest energy level, but sometimes from a lower energy level as well. Remember I said once you get past group 3, you get into extra orbitals and things like that, and so things get much more complicated. It's also true for metals of representative elements in group 4A and 5A. Most notably for us, lead and tin are 2 examples of representative group elements that can have more than 1 charge. So if we have elements that can have more than 1 charge, we have to indicate what that charge is, because something like iron 2 oxide is going to be a different compound from iron 3 oxide, and so we need to have a way to distinguish that. So if we're talking about iron, some iron is in the +2 form, but others have it in the +3 form. Copper is another common element, and that has copper in a +1 form. There's also copper in a +2 form. When a metal can form 2 or more types of ions, it has a variable charge. So we can't predict the ionic charge from the group number like we could for the representative group elements, or group 1A, 2A, 3A, etc. For metals that have 2 or more ions, we use a different naming system, and we indicate charge with a Roman numeral in parentheses. That comes immediately after the name of the metal, and there's no space between the first parenthesis and the name of that first that cation. So if we have a compound that has iron with a +2 charge, then you name that as iron 2, and you write it as iron with a 2 in parentheses. Again, no space in between right here. There is, however, when you write the anion, there's a space again in between the cation and the anion. If we're talking about iron with a +3 charge, then we're talking about iron 3, and we would pronounce that as iron 3. Transition elements almost always form more than one positive ion. The two exceptions that I want you to have memorized are that zinc and silver only have one charge. They only can form that one ion, and because of that, you do not use a Roman numeral when you are talking about zinc or you're talking about silver. Cadmium is also in there, but it's not as common, and so we're not going to focus on it here. Again, metals in groups 4A and 5A also form more than one type of positive ion. Most notably, we want to remember lead and tin here. Lead and tin can both have charges of +2 or +4, and then bismuth, which is in group 5A, can have cations with a +3 or a +5. Bismuth, not as common, and so I don't need for you to memorize those ones. If we visualize this on a periodic table, you can see in the middle we have all these transition metals. Most notably, what I want you to know is manganese, nickel, zinc. These usually have just one charge, but I really want you to know that it's silver with a +1 charge always, so you don't indicate it, and zinc has that +2 charge. And then your two that I really want you to know that are representative group elements but can have variable charges are tin and lead. So again, when you are naming these, you have to name them with a Roman numeral to indicate the charge. There's also another way to name these. This is a lot less common, but I do want to make you aware of it. When you have a cation that can form more than one ion, there's two different ways to name that. You have one that has a lower charge and one that has a higher charge. When it has a lower charge, a common name can replace that with an OUS ending for the suffix, and for the higher charge cation, so in this case iron 3, you would use an ic ending. So iron 2 is also called ferrous, and iron 3 is called ferric. These are a lot less common. Again, just remember if there is a higher charge, there's an IC ending and an OUS ending for that lower charge. If you notice that this beginning part really matches what the symbol is, and so you can imagine that the common name comes from, or the symbol comes from that common name, but you don't see it as much. So here you can see some of those common elements, metal ions that form. So again, here you see that iron 2 is ferrous and iron 3 is ferric. You can see copper 1 is cuprous and copper 2 is cupric. Again, you can see how these common names and the element symbols kind of match up better than what the English name is for them. Okay, so when you are naming compounds that have variable charged metals, again, you need to make sure that you use a Roman numeral to indicate. So let's jump in and do a couple of examples from this table right here. The first example that we'll go over, the compound that they give us is FeCl2. And so we know that iron is one of those metals that can form more than one charge, more than one ion, and so we need to indicate what that is when we name it. So how are we going to go about figuring out what the charge is? Well, we have two pieces of information here. We know that we're dealing with iron. We know that that can have more than one charge, but we also have chlorine in this. And we know that chlorine only forms one ion, and it's the chlorine -1 ion, the Cl -1. Because it's in group 7 and it wants to gain that one electron. And so if we indicate that, we know that chlorine has that -1 charge. Now, there's two of those, and so overall on my chlorine, there's a -2 overall, right? Because there's two of them. And so that means that in order to make a net 0 charge, the charge on this iron has to be +2, right? Because the +2 and the -2 are going to give me that 0. And so I was able to kind of deduce what the charge was on that iron by looking at what it was attached to and in what ratio they were attached. So now when I go to write this, I'm going to write the name of my cation, which is in this case iron 2, and then I write the name of my anion, which has that IDE ending. And so this is iron 2 chloride. We can do the same thing with, say, a compound Cu3P. Okay, so I know Cu is copper, and that copper is a transition metal that can form more than one ion. It forms a copper 1 and a copper 2 ion. And so we can look at phosphorus to help us determine what the charge on that copper is. Well, phosphorus, if we pull up our periodic table, is right here in group 5, meaning that it's going to have a -3 charge, right? It's going to need or want 3 electrons, 1, 2, 3, 1, 2, 3, to become like argon, and so it's going to be P -3. Well, if this has a -3 charge, that means that overall on our copper, we need to have +3 overall, right? But there's 3 of them. And so if each one of those coppers has a +1 charge, and there's 3 of them to make overall +3, then net the charge on this would be 0, which is what we want. Now when we go to name that, we're going to name it copper, because it's copper. It has a +1 charge, and so we're going to, in parentheses, put 1, and then we're going to name this phosphide. If we're looking at those common names, we can look at common names for both of these. When we're talking about iron, it's Fer for the start of it, and then we know that iron can form iron 2, and it can form iron 3. This is iron 2, which is the lower charge of the 2, and so we would call this ferrous chloride. If we're looking at the common name for our copper 1 phosphide, we know that copper can have a +1 or a +2 charge. This is copper 1, which is the lower, and so we're going to call this cuprous phosphide. Notice that that anion name just stays the same. All right, let's do one more example. We can do PbS2. Okay. Lead, again, is one of those metals. It's not a transition metal, but it can have more than one charge. And so we need to use our sulfur to help us figure it out. The charge on sulfur is -2 because it's in group 6A. There's 2 of those at a -2 charge, so overall we have a -4 right there. And so to balance that out, our lead needs to have a +4. And so when we name this, we're going to name this lead 4 sulfide. So when you come over here, you can see that the systematic names are all listed here for the examples. Okay, so just to kind of sum this part up, anions again are going to be named by replacing the ending of the element name with the suffix IDE. So you can see that bromine forms the Br- ion, which is bromide, and phosphorus forms the P-3, which we know is phosphide. We can also go backwards, right? We can be given the name of an ionic compound, and we can use that to write the formula. So in the first part of the name, you're going to describe the metal ion, including its charge, and the second part of the name is going to specify the nonmetal, and our subscripts are added to balance charges. And so when we do that, in this example, we want to write the formula for tin 4 oxide. And so this is going to walk us step by step through that. The first thing we want to do is identify what our cation is and what our anion is. Our cation is going to go first always, and our anion is going to go second. And so tin, because it can have more than one charge, when we are given that formula name, that charge is already given to us, so that makes it really nice. And so we end up with Sn, which is the symbol for tin, and it has a 4+ charge. For the anion, we have oxide, so that is oxygen with a -2 charge. If we look at oxygen on the periodic table, it's in group 6. It's going to want to gain 2 electrons to make 8, and so that's where that -2 charge comes from. Now what we have to do is balance those charges. And so in order to balance these out, right, we have a +4 charge here, but only -2 here. And so we need 2 of these. So if we put a 2 here, overall we would have a -4 charge to balance out with this +4 charge. And so our final answer is going to end up being SnO2. So we just have another example here. We're going to write out the formula for iron 3 chloride. And so when we analyze it, we know that iron 3 is going to be Fe with a +3 charge. Chloride is Cl with a -1 charge because it's in group 7. And so in order to balance those out, the +3 charge has to be balanced out with 3 of the -1 charges from chlorine to make a 0 net charge. And so when we write that, we write FeCl3. Keeping in mind that when we write this out, we don't include any charges. We don't include a 1 if there's a 1 subscript. Those are both incorrect to include those. Okay, the last thing that we have to talk about in this section is polyatomic ions. So a polyatomic ion is a group of covalently bonded atoms with an overall ionic charge. And so what that means is you have elements bonded together in a covalent form, but overall they have a charge on them. And so when these polyatomic ions participate in compound formation, they stay together as one unit with the charge of the overall ion. So if we're talking about an ammonium ion, ammonium is always NH4 with a positive charge. That NH4 is going to stay together. It's going to act as an ion so when you're going to balance out charges, you put that subscript with the whole group. So nitrate is NO3 with a minus charge, carbonate is CO3 with a -2, and you can go on and on with these polyatomic ions. The names of common polyatomic anions, so typically you're going to see one that ends in 8, so NO3 minus is nitrate, PO4 3 minus is phosphate, and when those have one less oxygen, then they end in ite. So nitrate is NO3 minus, nitrite is NO2 minus, so you can see the 8 ite. 3 oxygen, 1 less oxygen here. Notice that when we're talking about nitrogen-based compounds, the charge on both of these is minus. So what we're doing right now is we're just looking for some patterns within these so that when you go to memorize them, because yes, you do need to memorize the polyatomic ions, looking for patterns is super helpful. So these nitrogen-based ones have that -1 charge, and then NO3 is nitrate, one less oxygen, nitrite. You can see that same pattern follows with phosphate. So phosphate is PO4, 3 minus, one less oxygen, PO3, 3 minus, is phosphite. Both of these have a -3 charge. The way that I remember this is phosphorus is in the 5th group on the periodic table, and so those typically have a -3 charge, which matches that. But notice that that does not follow for nitrate, so you can only use that for phosphorus, and then also sulfate has that same pattern. So right here, you can add a hydrogen onto the beginning of these and use the prefix hydrogen or bi. So HCO3 minus, we would call that either hydrogen carbonate. So CO3, whoops, sorry about that. So CO3, 2 minus is carbonate. You throw an H on the front. When you add that hydrogen, the charge goes up by 1, and you call it bicarbonate. This would be hydrogen sulfate or bisulfite. So these are just some names and formulas for common polyatomic ions. OH minus is hydroxide. This is one that you definitely need to remember. Nitrogen-based ones, again, we have NO3 minus and NO2 minus, so nitrate and nitrite. The other one with nitrogen, and this is a unique one because it has a plus charge instead of a negative charge like all of the other ones, but NH4 plus is ammonium. For the chlorine-based one, we have ClO4 minus is perchlorate, ClO3 minus, so one less. Oxygen is chlorate. Another oxygen less is chlorite, and then hypochlorite is minus. The two here that I want you to know are the chlorate and the chlorite. For the carbon-based ones, CO3 2 minus is carbonate. HCO3 is bicarbonate or hydrogen carbonate. This is going to be another important one. CN minus is cyanide. You'll want to learn that one as well. And C2H3O2 minus is acetate. You might see this as CH2C. Oh my goodness. Never mind. For our sulfur compounds, SO4 2 minus is sulfate. You add a H on front, the charge again goes up 1, and you can call that hydrogen sulfate or bisulfate. You get rid of an oxygen, the charge stays the same, but you're going down in 1 oxygen, and you can call that sulfite. Add that hydrogen on, and you can get bisulfite. That same pattern follows with the phosphorus-based ions, and yeah, you're going to want to memorize all of these. When you name compounds, when you write the formulas for compounds with polyatomic ions, you're going to want to do it the same way, really. So when the charges equal out, so here we have sodium ion and we have nitrite ion, and so the plus charge and the minus charge balance each other out, and so we just have NaNO2. This would be sodium nitrite. So you just name it as it is. So sodium and nitrite, this is nitrite. With this BaSO4, barium, this is actually incorrect. Barium is in group 2 and it has a +2 charge, and so those balance each other out, and so you would have BaSO4 with a 0 overall charge. When the cation and the anion have unequal charges, you're going to do this exact same way that you would. The only difference here is you're thinking of this as one unit. Sometimes I like to think of this as like, okay, if I substituted this with an X, how many X's would I need to balance out? The answer is 2, but because it's a polyatomic ion, you have to include parentheses around that polyatomic ion if there's more than one. But magnesium with a +2 charge means that we need 2 OH- anions. This is a hydroxide anion to balance that out, and we get MgOH in parentheses 2. Notice that this 2 goes with everything in the parentheses. That means that there's 2 oxygens and 2 hydrogens here. The 2 does not just go with the H, which is why we need the parentheses to indicate that that's a polyatomic ion that stays together. When you name these, you're simply going to name the cation and then the anion. You don't have to specify the charges on these ions because they always stay the same. You don't need to specify how many ions of each type are needed to balance the charge either. And so if we are looking at sodium bicarbonate, HCO3 minus, HCO3 minus is the bicarbonate ion with an overall -1 charge. Sodium has a +1 charge, and so those charges balance out. If we look at aluminum sulfate, aluminum has a +3 charge and sulfate has a -2 charge, and so here's where we would do that kind of crossing trick to figure out the formula. Okay, so doing some practice problems with the polyatomic ions. Say I wanted to name something like CaCO3. Well, the first thing that I need to do is recognize that CO3 is one of my polyatomic ions. That is a carbonate ion, and so when I name this, the first thing I need to do is look at my my cation and say, okay, calcium. When I name my cation, I'm just going to name it as is, and so I'm just going to name this calcium. Now I already told you that CO3 is carbonate, and so all I'm going to do is say carbonate. Again, the key here is that you have to memorize these. You look for the patterns and you learn them that way, but there's really no other way but to memorize them. But you'll start to see them, you'll start to recognize, okay, I'm pretty sure this is a polyatomic ion, and so I need to name it as such. So say I had something like KNO3. K I know is potassium, and it's my cation, and so I'm just going to call it potassium. And then NO3 with a minus charge is nitrate, and so I'm just going to name it as it is. So that is potassium nitrate. Now say I have something like Fe3NO33. So Fe3, I'm sorry, that's not what I wanted to write. Get rid of that. Okay. Sorry. FeNO3. Okay. So the first thing that I see when I look at this is NO3 is nitrate. That is one of my polyatomic ions. So the first thing I need to do is recognize that. The second thing that I need to do is realize that iron is one of those transition metals. It can have more than one charge, and because of that, I need to indicate what its charge is when I go to write the formula. In order to write what its charge is, I have to figure out what the charge is first. And so if I come over here, I know that nitrate is a polyatomic ion, and I know that it has a -1 charge. But I also know that there's 3 of them. And so overall, that 3 times the -1 gives me a -3 charge. Well, if this FeNO33 is a neutral compound, that means that in order to balance out the -3 coming from the nitrate, then the charge on that iron has to be +3. So when I go to name this, I would name it iron, start my parenthesis. The parentheses indicates what the charge is, and then I can name my polyatomic ion, which is nitrate. Let's look at something like Al2, Al2, SO4, 3. Alright, so the first thing I want to do is recognize that SO4 is a polyatomic ion. That is our sulfate ion. The other thing I want to do is look at my cation. My cation is aluminum. Aluminum is in group 3 on the periodic table. It can only have one charge, and so we don't have to worry about indicating its charge. The other thing that we want to notice is that this SO4, so here's a good example of why we have to have the parentheses if we want to indicate how many of something are. If we put this 3 down here, that's going to look like SO43, which does not make sense and is not a real thing. And so that is just really a good visualization of why it's important to have those parentheses there. The 3 also means that there's 3 of the sulfate ions, and so that SO4 is going to stay together, and there's 3 of them. But when we go to name this, we're just going to name it aluminum, because that's my cation. I don't need a charge because the charge on aluminum is always +3, and so it is what it is. And we can name our anion, and that is sulfate. So that is just aluminum sulfate. I can also go in the other direction and say I am given a compound name and I want to figure out what the formula is. So let's try something like magnesium hydroxide. Okay, so for magnesium hydroxide, the first thing I'm going to do is say, okay, magnesium is my cation. Its symbol is Mg, and then I'm going to look at the periodic table and say, okay, magnesium is right here in group 2 on the periodic table. It's going to have a +2 charge. The next thing I want to do is say hydroxide is my anion. Hydroxide is one of my polyatomic ions, and it has a -1 charge. And so when I do these types of problems, I automatically put my ion in parentheses, and then I can always get rid of them later when I go to clean things up, because I'm going to have to clean things up anyway. So now on my cation, I have a +2 charge. My anion has a -1 charge, and so in order to balance those out, I can do that crisscross type thing, and say, okay, I would need 1 of these, and I would need 2 of these. To balance that out, so I'd have +2 overall for my cations, -2 overall for my anions, and I can go ahead and clean that up and write a nice formula without the charges. I have to leave the parentheses because there's more than 1 of my anion, and I pull that 2 down there, and that is the formula for magnesium hydroxide. Say I want to do something similar for copper 2 nitrate. So we have copper 2 nitrate. So my symbol for copper is Cu. The nice thing when you have an element that can have more than 1 charge is when you're given the name, you also are given the charge. And so there's nothing to look up on the periodic table. So that's copper with a +2 charge. And then we say, okay, nitrate, that's one of my polyatomic ions. I have to memorize it. It's NO3 with a -1 charge. So I can go ahead and again do my crossing type thing. So there would be a 1 here and a 2 here. And if I want to simplify that, I can write CuNO3 2. That is my formula for copper 2 nitrate. All right, well, thanks for watching. I hope that you found this to be useful as we tried to make sure that everything was cohesive for this topic. As always, if you have questions, hop into office hours, ask in class, ask in lab, whatever it is that you need from me in order to make sure that you are understanding these concepts. And yeah, we will see you later this week.